All right, here are the video solutions for week 5, lessons 2 and 3 in unit 5. So the first one, the thermostat in an empty apartment is set to 65 degrees Fahrenheit from 4 to 5 p.m., 4 a.m. to 5 p.m., and then to 50 degrees from 5 p.m. until 4 a.m. And here's a graph of the function H that gives the temperature in the apartment X hours after midnight. So the owner decides to change to a new schedule, and they set the thermostat to change 3 hours later in the morning and the evening. So everything is going to get moved 3 hours later. So let's just put points here. If we move each point 3 hours to the, or 3 units to the right, that we can sketch the new graph by connecting those key points. So we have this graph then. This will be g of x. It has everything happening 3 hours later than it did before. So explain what h of 6.5 means. This means that at 6:30, 6.5 hours after midnight, the temp is 65 degrees. So if h is of 6.5 is 65, then what's the corresponding point on the graph of g? And we want to use function notation to describe the point on the graph of g. So the corresponding point on g would be, here's h at 6.5. There you can see at 6.5 hours, that's right here. You can see that the temp is 65, so the corresponding point on h would be this one here, and that's happening at 9.5 hours later. So g of 9.5 is equal to 65. So write an expression for g in terms of h. Well, g of x is equal to h of x subtract 3, because it's at 65 3 hours earlier. So this would be h of x minus 3. So 3 hours earlier than g, than x here, h of x is at that same temperature. So the second one, a pumpkin pie recipe says to bake the pie at 425 for 15 minutes and then to adjust the temperature down to 350 degrees for 45 additional minutes. The function p gives the oven temperature setting p of t in degrees Fahrenheit, t minutes after the pie is placed in the oven. Explain what p of 30 equals 350 means in this context. This would mean, so we're talking about minutes, so 30 minutes after it's placed in the oven, the temp is 350 degrees. Diego discovers that the temperature inside the oven is always 25 degrees warmer than the oven temperature's setting. The function b gives the actual temperature of Diego's oven. So if p of 30 is equal to 350, then what is the corresponding point on the function b? So let's see. Diego discovers that the temperature inside the oven is always 25 degrees warmer than the oven's temperature setting. So the function b gives the actual temperature. So if p of 30 is 350, then b of 30 would be 375. And I think that's wrong on and then we want to write an expression for b in terms of p. So b of t is equal to p of t plus 30, 25 degrees warmer. I'm pretty sure that's wrong on the key. Let me just check here. Yeah. We'll have to take a look at that. Okay, so here is the graph of y is equal to f of x for number 3. Y is equal to the f of x for a function f. On the same axis, sketch a graph of g of x equal to f of x plus 2. So plus 2, so every output then is every y value is what it's telling us is going to be two units above where it's at now. So I'm just going to plot a couple of key points here. Can't really see much, but something like this. And then on the same axis, sketch a graph of h of x. So h of x is f of x plus 2. So this is g. Now put h of x in a different color. So h of x is going to be f of x plus 2. So that means that if f of x is at 0, let's see, we're going to move it 2 units to the left. So I'll just take this point and move it 2 units to the left, right about there, and then give it the same shape. So this is h of x. And then how do the graphs of g and h compare to f? So g is 2 units up, and h is 2 units left from the original function. So if f of x is at negative 2 here, h of x is at negative 2 units before that. So you would have to write x plus 2 there. And if we're adding 2 to the y coordinate, it's just a vertical translation up or down. So just remember, this is always kind of counterintuitive. Well, it is. You would expect a plus 2 to be shifted 2 units to the right, but it's actually 2 units to the left. Number 4, the graph shows the height of a tennis ball t seconds after it's been hit. The function f models the height of the ball in feet. How high was the ball when it was hit? Looks like the height was 5 feet when it was hit. And suppose a second ball follows the same trajectory, but is hit from 7 feet off the ground. Sketch the graph of the height of the second ball on the same axis. So we'll just try and guess that 7. Whoops. And we're going to start here at 7 and go the same way. And then we want to write an equation for a function g that defines the height, g of t, in feet of the second ball hit from 7 feet off the ground in terms of f of t. So g of t then, we're adding 2 to the height, 2 to the y value. So we're just going to take f of t, that y value, and add 2. For number 1 in lesson 3, here's a graph of f and a graph of g. Express g in terms of f using function notation. So it looks like f is the black one and g is the blue one. And it looks like g is a translation to the left of f. And so g of t, or g of x, is equal to, so here g of x is 1. where f of x is 1 here. And so g of x hits this height 1, 2, 3 units before f of x does. And so it takes f of x 3 more units to hit that height. And so g of x would equal f of x plus 3 then. Tyler leaves his house at 7. To go to school, he walks for 20 minutes until he reaches school 1 mile away from his house. The function d gives the distance d of t in miles of Tyler from his house t minutes after 7 a.m. So this talks about snow days, which may be the thing of the past now that we have distance learning capabilities, right? So explain what d of 5 is equal to 0.25 means in this context. So let's see. So that would mean that at 5, let's see, 5 minutes into his walk, he is 0.25 miles from his house. On snowy days, though, on snowy days, Tyler's school has a 2-hour delayed start time, so it's 120 minutes. The function s gives Tyler's distance s and t in miles from home t minutes after 7 a.m. with a 120-minute delayed start time. If d of 5 is 0.25, then what is the corresponding point on the function s? So the corresponding point would be s of 125 then, right? 120 minutes later is going to be 0.25, I mean. And then letter C, write an expression for S in terms of D. So S of T is equal to D of T minus 120, because in the original, he was leaving at 7 a.m. Now he's leaving 120 minutes later, so 9 a.m. But he's so he's getting to this quarter mile mark, this 0.25 miles away from home, 120 minutes after he does originally. So it's d of t minus 120. So a new function n is defined by n of t is equal to d of t plus 60. Explain what this means in terms of Tyler's distance from school. So he's leaving home now 60 minutes earlier. because the time is, you're adding 60 minutes to it, so he's leaving 60 minutes. He's leaving home 60 minutes earlier. Number 3, here are the data for the population F in thousands of a city D decades after 1960, along with the graph of the function given by f of d is equal to 25 times 1.19 to the d. Elena thinks that shifting the graph of f up by 50 will match the data. Han thinks that shifting the graph of f up by 60 and then right by 1 will match the data. What functions define Elena's and Han's graph? So Elena thinks moving it up by 60, so let's see, what should we name those? We'll give it a G here. And so Elena's would be up by 50, so G of D would be equal to F of D plus 50. But Han thinks that we could do something different, so we'll have H of D, we'll let that represent Han. Let's do it in a different color here. And he thinks shifting the graph up by 60 and then right by 1. So he's going to take f of d and move it right by 1, which means we're going to subtract 1 from d, and then add 60. So this would equal 25 times 1.19 to the d minus 1 plus 60 then, is how you would write it out. So let me move this up, or shrink it down. And then use graphing technology to graph Elena's and Han's proposed functions along with f. And which graph do you think fits the data better? So we've got 25 times 1.19 to the d, and then we've got 25 times 1.19 to the d plus 50, that's Elena's, and then we've got 25 times 1.19 to the d plus 1, and then plus 60. So we'll go to our Desmos app and write those all out, or type them all in and graph them. So so the first one is the original, 25 times 1.19 to the x, and then we've got 25 times 1.19 to the x plus 50. And then we've got 25 times 1.19 to the x plus 1. Whoops. I better have to put that in x plus 1. Oops. And then we want to add 60. All right, let's see how they look. So our original doesn't look right. Let's see, what did I do wrong here? change our window here to go to 150 there, and then on the X we'll go to 6. See if that helps see it cleared up here. Not really. Oh, I got the wrong. Okay, here we go. Okay, so looks like here are the data in thousands of a city, along with the graph of the function given by. So this is the graph of this function down here. So Elena thinks that shifting the graph of this up will match the data. So which one will match the data better? So the data looks like it starts at just about 75,000 and goes up to a little over 125,000. So which one works best there? I would say this blue one with just shifting it up 50 would be a closer match than moving it and shifting it up 60. So let's go with that. We'll go with let's see, who is that? I think Elena is closer to the data, which are these dots here. So, and then number 4 here. Here's a graph of y is equal to f of x plus 2 minus 1 for a function f. So we want to sketch the graph of f. So minus 1 means that it was dropped down 1, and plus 2 means that it was moved to the left 2 units. So we want to take this graph and bring it up 1 and move it to the right to get the original graph. So bring it up 1, which might mean right about in here, and move it to the left. So this point right here, this inflection point maybe, we move it to the left 2 units. So instead of a little over 2, it'll be right here. So we'll make this inflection like that, possibly. I'm sorry. We want to move it up 1 and to the right 2 units because it was moved to the left. So up 1 would be right about here. And if we move this to the right, let's see, we'll put it right about here. So we would go through like that maybe. All right, and that's it. So if you have any questions, please stop into office hours. I hope this helped.